Hello calculus students, this is Mr. Miller and welcome to video 4E, more about implicit differentiation. Remember, implicit differentiation is a technique for finding derivatives when you're not given an explicit formula for y. It's for when you don't have a formula like y equals x squared or y equals sine of x. Instead, you have a function defined by an equation like here for this heart-shaped graph. When we have this sort of situation. Okay, so once you get the hang of this, it kind of goes the same way every time. Let's try it. Okay, so we're going to try it for this curve. We're going to find the derivative of the function defined by the equation x squared minus y cubed equals 0. The points x and y that satisfy this have a graph that looks kind of like this. And we want to find the derivative at the point 1, 1 right there. So we're going to follow these basic steps here as listed in our textbook. The first step is to differentiate both sides with respect to x. So we have three terms to differentiate. When we take the derivative of x squared, we get 2x. When we take the derivative of y cubed, we have to remember that y is a function of x. It's like having y of x to the third power, and we need the general power rule. So it's going to be 3y squared times y prime. So 3 times the inner function to the 1 less power times the derivative of the inner function, which is y prime, which is what we're trying to find, equals, we got to take the derivative of the right side. The derivative of 0 is 0. So we completed the first step there. The second step is to solve for y prime. We collect all the terms with dy dx or y prime on the left side and move all the terms that don't have y prime to the right. So we want to move this term 2x to the right side. So we subtract 2x from both sides. And when we do that, we end up with minus 3y squared y prime equals minus 2x. The third step is to factor out dy dx from the left side. Well, we only have one term, so we don't have to worry about that. And then solve for dy dx. It means divide by this. So if we divide both sides by that, we get y prime equals minus 2x over minus 3y squared. And at least we can simplify this by canceling the negatives. Negative 1 divided by negative 1 is 1, so that's equal to 2x over 3y squared. So if you give me the x and y coordinates of a point on the graph, for instance 1, 1, we can find the derivative there. Y prime equals 2 times 1 over 3 times 1 squared, which would be 2 over 3, or just 2/3. That's the derivative right there. Okay, I would like to practice the technique of finding the derivative. It seems like this is the part that's most important here and getting all this straight. So this first one is the derivative of x to the fourth. Well, x is what we're taking the derivative with respect to, and we just use the power rule. It would be 4x to the third power. This is different. This is the derivative of y with respect to x. And y is thought of as a function of x. So this is the same as y of x to the fourth power that we're taking the derivative of. So we need the chain rule, or more specifically, the general power rule. This would be 4y to the third power times the derivative of the inside function, which is y prime. So that's the difference between taking the derivative of x to the fourth and y to the fourth. Y is a function of x, and we need the chain rule. All right, so this one, we've seen this many times. The same as the derivative of x to the 1/2. So that's equal to 1/2 x to the minus 1/2. And if we rewrite that, that's 1 over 2 square root of x. This one is similar, but we got to remember that y is a function of x. So this would be 1/2 y to the minus 1/2 times the derivative of the function, which is y prime. Or we could write this as y prime in the numerator over 2 square root of y in the denominator. Okay, so notice the similarity here. But this one has a y prime, and this one doesn't. Right, the derivative of sine of x with respect to x is cosine of x. We know that one. Well, this one's similar, but we need the chain rule because it's the derivative of sine of y of x. There's a composition of functions here. So this would be cosine y of x, or cosine of y, times the derivative of the inside function, times y prime. Or, if we want, it's y prime cosine of y. Alright, well, I have some more of these. We'll go through these kind of quickly, but these are these top ones are with respect to y. So we need the general power rule. So this one would be 5y to the 4th times y prime. This one doesn't matter that it's a fractional exponent. This would be 2/3 y. When we subtract 1 from the exponent, we get minus 1/3 times y prime. Or we can write this as 2y prime over 3y to the positive third. All right, this one. This is a product, so we need the product rule. Remember, the product rule is f prime g plus f g prime. So here, f is x, g is y. So when we take the derivative, it would be f prime 1 times g, which is y, plus f, which is x, times g prime. Well, that's y prime. So we simply get y plus x, y prime. This is the product rule again. We'll let this be f here and this be g. So f prime would be 6x times g, which is y, plus f, which is 3x squared, times g prime, which is y prime. Okay, we'll leave it like that. This one, product rule again. This is f, this is g. So f prime would be 2x times g plus it'd be f times g prime. Well, we gotta remember the general power rule here. This is y squared, so its derivative would be times 2y prime. All right, this last one's really kind of tricky. We can think of this as the derivative of xy to the 1/2. So it's a combination of the power rule and the product rule. So this would be 1/2 xy to the minus 1/2 times the derivative of the inside, the derivative of xy. Actually, that's what we figured out over here, so I'm just going to copy that. But we need the product rule for that. So it'd be y plus x, y prime. So altogether, we have y plus x, y prime in the numerator. And we have a 2 in the denominator. And this is going to go in the denominator for 2 square root of x, y. That was definitely the most tricky. All right, now let's use all of this. So several examples of implicit differentiation. So remember the first step, we're going to take the derivative of all the terms. Okay, so this first one, we would get 3x squared plus the derivative of y cubed, 3y squared y prime. Don't forget the y prime. Minus 6 times the derivative of xy. I need the product rule for that. So it's minus 6 times whatever I get for that. So remember, it's f prime, which is 1, times g, plus f g prime. And the derivative of 0 is 0. Okay, so we did the calculus part. So now I'm going to do some algebra. We want to get all the terms of y prime on the left, the terms without y prime on the right. So if I distribute, I get 3x squared plus 3y squared y prime minus 6y minus 6x y prime equals 0. So this term and this term have to go. They're going to go on the right side. And the second term and the fourth term can stay. So we get 3y squared y prime minus 6x y prime equals minus 3x squared plus 6y. They change signs because I moved them to the other side. Now we got to do step 3, factor y prime out of the left side. So this would be y prime times 3y squared minus 6x equals negative 3x squared plus 6y. Then we divide both sides by that, and we get y prime equals minus 3x squared plus 6y divided by 3y squared minus 6x. Now, sorry, it's supposed to be an x there. Now, we're supposed to find the slope of the tangent line at this point. So that's a crazy fraction, so I'll save you the trouble. If you just carefully put those fractions in for x and y and use your calculator, you get y prime is 4/5, which is 0.8. And that's the slope of the tangent line at that point. Okay, let's try it again for a circle. So this one's going to be, I think, a little bit easier. So for the circle, we're going to need the general power rule twice because we have a function to a power here and another function to a power here. So here we go. The derivative of the first term would be 2x plus 1 to the 1 less power times the derivative of the inside, which is 1, plus, same thing here, 2 times y minus 2 to the first power times the derivative of what's inside. You gotta remember, y is a function of x. The derivative of what's inside is y prime. Okay, equals the derivative of 20, which is 0. Okay, so if I write it without the 1's as the exponents, it's a little simpler. I have 2 times x plus 1 plus 2 times y minus 2 y prime equals 0. Well, I'm going to move this to the other side. Equals negative 2 x plus 1. And really, I just got to divide by this stuff here. And I've done it. Solve for y prime. So y prime is minus 2 x plus 1 over 2 y minus 2. The 2's cancel. So I have minus the quantity x plus 1, so I'll distribute that. We got minus x minus 1 over y minus 2. And then we want to evaluate it at the point 3, 4. So we can put 3 in for x, 4 in for y. We have y prime equals minus 3 minus 1 over 4 minus 2. I get minus 4 over 2, which is negative 2. So that makes sense. The slope looks like it's negative right there. That's the slope of the tangent line there. All right. I got 2 more examples for you. And this takes a lot of practice, so hopefully these are helping. Here's this really weird kind of curve. It looks like a piece of string lying in the xy plane. And we want to find the derivative right there at the point 0, negative 2. To do this, we're going to need the power rule here, the product rule here, and the general power rule there. Okay, so here we go. The derivative of the first term is 3x squared minus, okay, I need the derivative of xy. We've done that already a couple times. We found out that is y plus xy prime. So that's the derivative of xy. Then plus the derivative of y squared is 2y to the first y prime. and that equals the derivative of 4, which is 0. Okay, I'm going to distribute 3x squared minus y minus x y prime plus 2y y prime equals 0. These first two terms got to go on the other side. So that equals minus 3x squared plus y. Got to factor out a y prime. So that's y equals minus 3x squared plus y. And then divide. So after a while, this gets pretty routine. It follows the same basic steps every time. So although, equations are different, sometimes the derivatives are tricky. Take the derivative, solve for y prime, plug in the point. It always goes like this. So when we plug in 0 for x and negative 2 for y, we get negative 2, because this first term will be gone. And negative 2 is what y equals. Divided by minus x is gone. 2 times negative 2 is negative 4. We get 1/2. Kind of makes sense. Looks like it's about 1/2 there. That's the slope of the derivative there. All right. Thanks for hanging in there. We have one more example. This one has square roots. So we'll use kind of a previous work we did on earlier pages. The derivative of square root of x, well, we know that to be 1 over 2 square root of x. We did that earlier. Plus the square root of y. Remember, we treated that as y to the 1/2 and used the general power rule. And we got y prime over 2 square root of y. That's the derivative of that. Equals 0. Okay, this term's got to go. So we get y prime over 2 square root of y equals minus 1 over 2 square root of x. I moved it to the other side. I'm going to multiply both sides by 2 square root of y. So times 2 square root of y. And those will cancel. And we get y prime equals minus 2 square root of y over 2 square root of x, which is minus square root of y over square root of x. This one wasn't bad at all. Okay, so now if we plug in the point, 16 for x, 25 for y, we get y prime evaluated at 1625 is minus the square root of 25 over square root of 16. Well, that's just minus 5 over 4. Done. Wow. All right. And that's the derivative at the orange point right there. Okay. So time for you to try your hand at this. I got just one for you. This is kind of a weird shape. It's not quite an ellipse. It kind of has an oval shape, but it's not really an ellipse because of this y to the 4th term here. Anyway, what you need to do is use implicit differentiation to take the derivative of both sides, solve for y prime, and find out what it equals at the point 5, 2. All right, show all your work. See you in class.